result from the past today, but it's a problem from the past that I don't think I did. And I didn't do it deliberately because you'll be reminded of the context of the problem we're doing today. So what I want to do is example 7.9. So that's the previous chapter. And it is, I should do this more often. I should do few problems from the back in every chapter so that we refresh sort of some of the central points. So this just happened to work out that way, but I think I've learned my lesson here, but I haven't done it yet. But as I think through it, we should constantly visit some of the older lessons. So, you recall Faraday's law, and I'll tell you what this problem is. Minus dB dt. It has an integral version. It is E dot dl, because I can use Stokes' theorem. And I can also bring this out, and I get V dot dA. So by that I mean, if you have any dA, oops, that's not quite normal, and if I integrate and compute the magnetic flux through a certain area, mindful of Stokes' theorem, I should pick an orientation on the boundary and do an integral of dl. So this is what connects the two. And we've gotten into the habit now, we don't have to make apologies for it, that is quasi-static approximation, largely because we're able to do a few problems analytically, otherwise the discussion would be just closed and we'll miss out on a good bit of physics. And you will see where such approximations go bad. So this is also a reminder of, hey, be careful of what you're doing. So what you have here in this problem, this is example, what's that, 7.9, you have a current. But this current is a function of time. So, as you know, magnetic field would, if the current weren't a function of time, the magnetic field would curl around the wire using Ampere's law, and it would be mu 0 I over 2 pi s in the phi hat direction. And the quasi-static approximation simply says this is a function of t. So we'll just assume that the change of current in time is not so fast that we can use this approximation. This continues to be the expression for B. Okay, now B is a function of time, so this occurs. So obviously, there's going to be an E that is generated. And we have to pick an area and a loop so that Stokes' theorem applies. Okay, so I'm going to, just to get away from all of this diagram, I'm in particular going to look at this point, for example, and B is into the board. So my dA is going to be into the board for an easy flux and an easy path to integrate over would be this. And if I have to integrate this way into the board, my orientation better be I'll pick or the other way around. Yeah, this is that. So yeah, you're right. Thank you. So we're all creatures of habit. this way. Correct? I'll call, for lack of a better distance notation, I'll call this S0, Griffiths does, and this will be the point distance S. So then let me write the integral. I expect E to be, the component of E in this direction, to be constant. It cannot depend on here or here. So some E S0 times L minus E at S times L is equal to minus, I'm going to take the time derivative because I can just write it as I dot 2 pi S, no, not S, this is ds, and that, well, that length is just L. So I'm going to get ds over S times the, and this is from S0 to S, and times L. Now, I didn't include this component. If it did exist, you can talk yourself out of it very easily. It doesn't, but if it did, it would cancel. Electric field here and electric field here has to point exactly the same way. This is going that way, this is coming this way. Okay. Good. And so I would have what? Minus mu 0 I dot over 2 pi times L natural log of S minus natural log of S0. And so the electric field, now I can write it as a vector, as a function of S. Look at what I'm doing. So this is, first of all, the L's would cancel. And I just, see, this is a negative term. And this is a negative term. So what I could do is it becomes minus mu 0 I dot over 2 pi natural log of S plus some, I don't know what they want the constant. So let me factor. Yeah, so this is minus, this is minus, so I don't need the minus, right? Plus some integration constant. I use K because Griffiths used K, nothing special about K. This is Z hat. Make sure my expression is correct, and it is. Yeah? Some constant. I mean, we have this S0. This is the expression for the electric field. This K is not a function of S. Nothing prevents it from being a function of time. So what happens as S goes to infinity? What does the graph of natural log look like? So as S goes to infinity, electric field, the magnitude of the electric field is going to infinity. Just because you have a wire here That's not reasonable. That is quasi-static back. Because if you perturb an electric field here, there's some propagation of electromagnetic fields that propagate outward, that modifies the electric field. And the further out you go, the further out we'll see in chapter 9, the next chapter, that electromagnetic disturbance propagate at the speed of light. So in time, it's going to reach far enough away and modify the electric field, perhaps. So we cannot use quasi-static approximation blindly. We have to keep things in mind. So I'll use this result today. So when I use it, you know where it's coming from. And also, it's good to visit quasi-static. Okay. We have any questions? Martin, Chip? We've had a couple of conservation theorems. I'm going to write it down for my own sort of recollection. So first was dW dt. This is the rate of doing work. That was equal to, and I'm using this divergence version, so it is a d tau, meaning this can be easily converted to a dA, d tau minus, what was it? I forget the exact. I think it was just S, and then we have to be careful what S was. Yep. S dot dA. So this is obviously work, rate of change of work per unit time. So this is like the power term. Okay, and S was 1 over mu naught E cross D. So it's the energy per unit area, energy flux per unit time, energy transmitted, if you will. Because this times that, the area is the total energy, so it's per unit area, per unit time. It's also written as energy flux. Per unit time. I guess you could say power flux. I don't recall hearing that term. We had a close cousin of this, which is the net force. And that was also but the factor here differed slightly, minus mu 0 epsilon naught S d tau. Is this expression correct, guys? Please make sure that I'm thinking correctly. We've had far too many expressions. Oh, there's a ddt. Sorry. In fact, mu 0 epsilon. Huh. Do I have? Oh, sorry. You were right. This is not that. Where U equals 1/2 epsilon naught E squared plus 1/2 mu naught below v squared. This is what we have. So work done on charges is equal to rate of change of work on the fields. Oh, I have to be careful here. Minus. So let me write that carefully. I'm mixing terms. I shouldn't. dt minus. This is the expression. So please check. Again, like I've said, we've had so many equations that I get terms mixed up. Check. Then we have this expression. We want to make sense out of this. The whole thing got started because we wanted to talk about momentum. So is this very good? Which one? There are several versions of it. T dot dA is the same thing as divergence of T d tau. Yeah?
There's so many rules.
I mean, no, it's the divergence theorem. Yeah. So in fact, you know what? We will do it that way. So force is rate of change of momentum, but it's the mechanical rate of change of momentum. Let me write it exactly the way you said you prefer. T dot dA. I'm going to do it the other way. Plus d dt of mu 0 epsilon naught s d tau equals T dot dA. Would this be correct? I wrote this force as a rate of change of momentum. I brought this term to the other side. Here I use the divergence theorem to write it this way. Now, I have an interpretation here. The momentum of the charges means I can do this. Momentum of the electromagnetic field is outside of this derivative. See, they're both ddt. Another thing I've been doing is putting vector arrows on everything. Does that interpretation grab you meaningfully? Because then I would have on this side ddt, total momentum, yeah? Conservation of momentum is what we have. So this would be 0 unless this would be 0 if this is 0. So obviously this has to do with the flux of momentum. Yeah? For the total momentum to decrease, this has to be a negative quantity. Yeah? That means, what is momentum flux? Rate of change of momentum flux is the negative of that quantity. See, here, and this is the reason I really wrote these equations down. Look, I'm going to do, gosh, how many times can I write it incorrectly? This is power. This is total energy. There has to be a time derivative there. Yeah? So look, and this is an equal to sign. Watch this. If this is the flux, there has to be a negative sign. So what is the flux of rate of change of momentum? It's given by minus look, the reason I'm doing that is I'm comparing this to this. For it to be a flux, there has to be a negative sign here. The only way I can get a negative sign here is I put a negative, and then I put negative. So this negative is the flux. So if this is positive, this is negative. Therefore, the momentum decreases in time. There's a symbol G. This is the momentum density of the electromagnetic field. Momentum that is precisely, it's the density, so it's without this integral. So you can see all these symbols just let me stare and make sure I have not made any mistake. Rate of doing work mechanically plus the rate of change of electromagnetic field energy is equal to the flux of power, where S is given by this quantity. This is the Poynting vector. Fine. What is the energy density of the electromagnetic field? That is the energy density of the electric field plus the energy density of the magnetic field. Then we computed the force, and then we choose to rewrite it in the same sort of energy conservation with flux point of view. And when we do, we write F as dp dt, mechanical, bring the other time derivative to this side, and leave this, well, we used divergence theorem to write it as a dA so that we have a flux term. Okay? So if we identify this quantity as field momentum, and we would have that the total change of field momentum plus the mechanical energy, we want it to be conservation, so we want it to be zero unless there's a flux, unless it is escaping your region and it's going out somewhere. Now, if you integrate over all space and then t goes to 0 as we go to infinity, we do indeed get conservation. But mind you, we don't have to get a conservation. Unlike planetary motion, we could have a plane wave that goes away to infinity forever. If we do, we're losing energy to infinity, so to speak. Yeah? Okay, so therefore, this term with the negative sign, don't forget, is interpreted as the flux of momentum. And whatever is here without the integral is the momentum density. Because when you integrate momentum density, you get the total momentum. And that's this guy. And what happens is the mu zero cancels because of the denominator. And then what remains is epsilon naught. So this E cross B has two interpretations. Modulo a proportionality factor, so that the units are just right. In this case, it is energy flux per unit time. In this case, it is the momentum density. When it comes to fields, if there is energy density, there is momentum density. Yeah? I'm going to shock you with that. I'm going to erase this. You'll have to tell me what the correct equations are. It's one thing to develop it. It's another thing to keep all this committed to memory. It's a waste of memory unless you're constantly working on it. You pick it up as needed. There's only so much information that you can keep in your brain. You know, Watson from Sherlock Holmes one day informs Sherlock Holmes that the Earth goes around the sun. And I mean, this is back in the day, it's news, right? So Sherlock Holmes says, great, now that I know it, I'll try my best to forget it. Because he wanted all the pertinent information with regards to crime in London. He could tell you where the cigar was purchased by looking at the ash from the cigar, right? So you really don't care if the Earth goes around the sun. Unlike Galileo, who cared about such things. So we all have to live in our own little bubble of information. So let me illustrate this point and see what happens if I can do this problem. So let me explain this problem as well. This is example 8.3. So what you have is what Griffiths does best. You have two conducting infinite concentric cylinders, one of radius A, the other of radius B. There is a plus lambda charge, linear charge density glued onto this one. And then he puts a minus lambda on the outer rim. And then what he does is he connects a battery from this side so that current flows between them, and you have to complete the circuit. So what he does over here is puts a resistor. So whatever current goes up returns to V. And we're going to do many things. We're going to use quasi-static. We're going to also assume it's an infinite conducting cylinder, so that we're able to talk about things meaningfully. So because of this charge density, there is an electric field outside. It is given by Gauss's law. So electric field will be proportional to S hat, normal to the cylinder. And it turns out it is, you've done this problem before, it's also in your freshman physics book, it is lambda over S. And there is a quasi-static B. At the moment, not quasi-static, it's just static. So I'll make that clear if necessary by putting a T over there, 2 pi S phi hat. So first things first, let's compute. When there's E and B, there's only one thing you can compute, which is what? The pointing vector. What is the pointing vector? 1 over mu naught E cross B. So E and B are perpendicular here. So the pointing vector is plus or minus Z. What is S hat cross phi hat? Z hat. Mu 0 goes away. Then I would get a lambda times I 4 pi squared S squared. Is that true? Correct. Huh? Yep, we are. The mu naught goes away. Good. Thank you. So, let's compute the power. Power. Oh, by the way, again, you've done this problem before. If you use this and take the negative gradient of this, you'll realize that the potential difference, we have solved this before, between the two conductors, V is lambda over 2 pi epsilon naught natural log of B over A. We've seen that before. So let's compute the power. Power is nothing but energy flux per unit time, but you integrate over area. So this is S dot dA. So what area am I going to integrate over? So I'll pick a cylindrical area where E cross B exists. So that is correct? So power crossing, oh yeah, well, so I should do this.
Okay.
Yeah, but not inside the small cell. Yeah. Well, so that is going to be, first of all, vector S and dA is along the z hat direction. Z hat dot z hat is 1. So I would have integral lambda I over 4 pi squared epsilon naught 1 over S squared S ds d phi. D phi goes from 0 to 2 pi. This goes from A to B. And I get what? Lambda I have a 2 pi from d phi, so I get back to 2 pi epsilon naught. And it becomes ds over S. And so I get natural log of Yeah? Lo and behold, yeah? Not disturbing. We continue to move on. Let's compute, sorry, the total momentum. Momentum of the field, EM, is, what is it? It is G d tau, momentum density d tau. Correct? And I just erased it. What is it? Epsilon naught mu naught? Epsilon naught mu naught S d tau. And let's, consider a cylinder of length L. L being large enough to where we can use the infinitely long cylinder approximation. And so I take this and multiply by epsilon naught mu naught, and the epsilon goes away and mu naught sticks around. So I would get mu naught lambda I over 4 pi squared. S is pointing in the z hat direction. 1 over s squared. What is it? S ds d phi dz. You know the calculations, so I'm going to do this. 4 pi squared, oh, that's a funny looking 4 pi. I get a 2 pi from d phi, correct? So this becomes back to 2 pi. I get an L from dz. Again, once again, I get a natural log of b over a. Everyone good with the natural log of b over a? It's ds over s is natural log. The inner radius, outer radius, b over a. And z hat. He writes it in an interesting way. We don't have to necessarily do that. He brings in C, because remember, C is 1 over epsilon naught. C squared is 1 over epsilon naught mu naught. But and what does, yeah, so let's do that. What is my, so what I'm going to do is put epsilon naught here and epsilon naught here, and then what is this? That is the potential, right? So that is V I L over C squared Z hat. Correct? This is a static field. What is this momentum? There's E, there's B. There's something going on here. Any thoughts?
That's opposed to E being a function of time and B being a function of time.
No. At the moment, this is static.
Right. I mean, if it wasn't, there'd be some kind of.
Okay, then we can begin to believe that.
Okay.
But in the static case, yeah, we have no idea why this is the case. This is relativity. Light cannot stand still. And there is a relationship between energy, momentum, and energy and momentum of a particle. For something traveling at the speed of light, for it to have its rest mass being zero, because photons don't have mass, if there is energy, there has to be momentum. It comes from special relativity. It's an early sign of what's going on, the breakdown of normal intuition. So here is something that just stands still. But, okay, so what I want to do, let's remember this expression, which I'm going to promptly erase, and try to make sense out of this. So now you make indeed you dial down the current so that the current goes to zero. Time dependent. So that I slowly goes to zero. Slowly enough to where there's a quasi-static B. If there's a quasi-static B, there's an electric field. We just saw it. The previous example I did from the previous chapter. So what's the electric field? So from Faraday's law, E u0 over 2 pi I dot natural log of A plus K in the z hat direction. Remember, we just did that. So this electric field is going to act on this charge and this charge. It's going to push this charge up, and this is going to push this charge down. So then the force on the charges is given by, I'm just going to write it quickly with time in mind. On this entire charge, so it is lambda times L, mu 0, oh, this is natural log of S here, mu 0 over 2 pi, I dot natural log of positive charges in the inside place, inside the cylinder, and there's a minus lambda L, mu 0 over 2 pi, I dot natural log of B plus K and I'm going to simplify that expression. In fact, the constant term goes away and this becomes a natural log of B over A. I get that my force, a little bit of a hurry, force is equal to minus mu 0 lambda L over 2 pi I dot natural log of B over A z hat. Therefore, the momentum delivered onto, the force acting has to be counteracted, right? So what is the momentum delivered? Well, that's minus, the force decreases with respect to time. So this becomes minus and minus cancel, so I get mu 0 lambda L 2 pi natural log of B over A. It is in the z hat direction. Di dt dt. And what do you get? It is just I, because when you do this, it is I minus 0. Final I minus initial I. Oh, sorry, it's f dt, so there's a minus. So minus mu 0 lambda L 2 pi is final I minus initial I. Because if you have ddt over here, what can you do? That's just final I minus initial. Current is going to 0, so 0 minus I, and this cancels, and then what do we get? Guess what? It was the other momentum. So the momentum could not have been delivered if it didn't have momentum to begin with in the first place. Yes, sorry. So it seems odd that a static system should have momentum, but when you dial it off, it is imparting this much momentum to the side. Somebody has to hold it in place by giving it an opposite force. So the question is, how could it impart momentum to begin with? There's no flux of anything, so it must have had the momentum in the first place. So again, the precise choice of topics and problems to illustrate the curiosity that something static can have momentum. E cross B, modulo constants outside, is both power flux and momentum density. Power is energy, energy per unit area per unit. Or it's the density of that. This contributes to energy density. It also contributes to momentum density. So if you take a parallel plate capacitor, where there's an electric field, and you put it in a magnetic field, there's a momentum. Somebody's fighting something to keep things in place.